Okay, here we go. Friction, yay! Friction opposes relative motion. Okay, we've kind of already talked about this. So friction does stuff. You have static friction when things aren't moving, kinetic friction when things are moving. This is in the previous videos. So something that's kind of interesting is because of a physics perspective. So basically, if you've got a box sitting like this on a surface, it was kind of drawn a little picture here that the friction technically, because you're like, well, the friction is based on the surface area, which is, so, I mean, if we were solving this in a really more advanced class, we might get into all that, but basically, okay, so pretend you have like itty bitty normal forces all the way around. Okay, so you have itty bitty normal forces, so like let's say this weighs 30 pounds or whatever. So each one of these is 30, and then we'll call this like 1 square meter or something. So it's 30 newtons per 1 square meter is the pounds, not pounds per square inch, but you know what I mean. It's the pressure. So what you can kind of think about is like each one of these itty bitty normal forces, itty bitty normal, itty bitty normal, itty bitty normals, are all bigger than if you did it like this, because there's more area to distribute it across. So all these are slightly smaller itty bitty normal forces. So the way that friction is defined is the force of friction. I don't know why I did an S there. The force of friction, whether if something is moving, let's just start with it moving, is given by mu sub k times n, times the normal force. So in theory, if you were in calculus, and this is where this eventually goes, is it would be like up, and then like this would be your pressure d area, and so these would be like all your itty bitty pressure-y thingies, dA, and you'd kind of integrate over the whole area. So if all those were different. So I guess where I'm trying to go here, if this is not obvious, is sometimes there's this thought of like, well, there's less friction if I tilt it up because there's less surface area. And it's like, well, that's not true, because there's like these normal itty bitty normal forces are all bigger. Now I know that the sum of all the normal forces, like the sum of the area under the curve of the normal forces, is the same. It's still going to be equal to, say, 30. And the sum of the normal forces here is all going to still be equal to 30. But each of the individual ones is bigger, so whenever you sum all the individual ones, and you multiply by a constant versus you sum all the itty bitty bitty ones, the more itty bitties, and you sum by a constant, it still comes out to be the same. So all that said, assuming the box is made of the same thing on all 6 sides, and assuming we're not getting into like deformation of the box or anything like that, it doesn't matter whether the box is up and down or side to side, it's still going to have the same friction, just because, well, calculus, but so you can either believe me because calculus, or you just believe me because I said so, but I mean, you can try it as well, but essentially changing the orientation isn't going to change the contact, even though you feel like, well, it has more contact, so it has more friction, except that those normal forces are smaller. So anyway, it's interesting. So there we go. So static friction is, again, the friction that's not moving. This is a really important formula, and I do feel like I always misunderstood it in college, is that anytime I would have something that was a static friction that was not moving, I would immediately be like, oh, static friction is equal to mu sub s times n, but it's not. That's the maximum, and I know that I've showed this in another video, but basically, like, if the box is sitting here not doing anything, then there's no static friction. But if I start pulling on it and it doesn't want to move, then it can resist. So if I pull on it at 20, it can resist to 20. If I pull on it in 30, maybe it can resist to 30. But maybe if I pull it on 40, it can't resist anymore, and then it starts moving, And now it resists at the kinetic friction, which is mu k sub n. So maybe at, come here, mu 40, or thing equal 40, now it's actually only resisting at, 15 or something like that. Because this, what do you call it? This is always bigger than that. So it's always harder to get something moving. I don't even know if it's ever even equal. Yeah, it's always harder to get something moving than it is to keep it moving. So I think the big thing that you have to do here is you never label the friction, the static friction, as its max. You just kind of write somewhere the friction has to be less than this value. And then eventually you get into questions like, well, if it isn't less than this value, then it's moving, da, 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 da. Unless it'll say something like, if it'll say impending motion, and then you're going to be like, oh, okay, now I can set it to the max because it means it's about to move, it's doing its best, it's maxing out, kind of a thing. So, doop-de-dee-doop-doop-doop-doop-doo. Doop-de-dee-doop-doop-doo. Oh, see, there's your little graph, see? So the force goes up until it's max. So if I'm not pulling on it, it doesn't respond. And then it responds, and it goes, ah! And then it's great. Okay, but that's like strength materials class, mechanics materials. Okay, and then here's a list of things that nobody's going to look at. Maybe you will, because you're really awesome. Okay. Ew, bones are gross. Okay, so a crate is at rest on a floor. We're going to push this crate. Okay. Crate. And he's 200 kilograms. 200 times, 20 times 9.81 is 196.2. So he's 196.2 newtons. Sweet. The coefficient of static friction between the floor and the other thingy, go back here, between the floor and the other thingy is, coefficient of static friction is 0.7 right there. And the coefficient of kinetic friction is 0.6. Okay. An additional force is applied to the crate. Okay. So we do have a normal force of the crate to the floor. And then we have this force here, P. Alrighty. So since the, what is this thing called? The crate is not flying into the sky. That means that the sum of the forces in the y direction is going to be 0. So I have negative 196.2 plus the normal. And I guess that's really important for you to know as well, is that it is just the normal force. It's not always going to be the weight. So right now, whenever I solve for this acceleration in the y, this is 0. So right now, in this case, the normal force is just the 196.2 newtons. But if I had a crate on an incline like this, then the normal force wouldn't be the whole thing, because wouldn't be the whole weight, because the weight is getting broken out into those two pieces there. Make sense? Okay. So that's what we're doing with that. Come back here. So do the math anyway. Always write out the sum of the forces in the y direction to make sure that you're getting the correct value for the normal force. Okay. So find the force of friction. Okay, so there's a frictional force that's preventing impending motion. So he's trying to go this way. Frictional force. I guess I should have written that earlier and I didn't. Okay, so some of the forces in the x direction are P minus F, and this is mass times acceleration in the x. So if I look at case A, come here, girl. That happened. Okay. So for case A, P, what do you call it? Magnitude of P is 20, and it's all in the I-hat direction. So I do know that the force of friction has to be less than or equal to mu sub s times the normal, because right now I don't know whether it's moving or not. So I'm going to come over here and do this off to the side. So F static has to be less than or equal to 0.7 times 196.2. Okay, so 137.34. So, okay, so if I'm not pushing at least that hard, it's not going anywhere. So, whoa. Okay, so if I'm going 20 minus the force of friction is mass, I already forgot the mass, whatever it was, 20 times acceleration in the x. Now, I can't just turn my brain off and solve this problem. So I can't just put 137 right here because that's the maximum value it can be. But the force of the friction is going to be anywhere from 0 up to 137. And so basically, I wish I had a better way to say this. This box isn't moving. And this is just one of those things when you have to understand what's physically going on in the problem. And that's why I always hate friction problems, because I just want to do math and not have to learn anything. But this box isn't going anywhere because it's not like friction is going to force the box backwards. The friction is going to, so I'm going to write here. So force of friction in this case, or let me actually write it this way. So since that's happening, so AX equals 0. So the force of friction in this case is 20, which is less than or equal to the 137.34. So we're good. It's not moving. Okay, is that kind of making sense? So sometimes what we'll do, especially when these problems get more complicated, is we'll make an assumption. So if we make an assumption like it's not moving, all right, and we have the sum of the forces in the x direction, so P is, now what is it, 30? Yeah, 30. 30 plus minus, yeah, 30 minus F equals mass times acceleration of the x. So if assumed that it's not moving, then this is 0 because of this assumption. So the question is, does Fx less than F max hold? So is it true? I mean, yes, it's going to be true, but is this true? And if it's true, then that means our assumption was correct. Does this kind of make sense? So 30 minus f of f is 0, so f sub f is 30. 30 is less than 137.34, so the assumption was correct. Not moving. Make sense? Okay, so now I'm going to do, well, 120 is going to give me the same thing, so I'm not even going to bother. But now I'm going to look at the next assumption. So the D, if I go assumption, I'm just going to show you what it looks like. Not moving. So if I assume that it's not moving, then that means the sum of the forces in the x direction were, what is it, 180 minus force of friction equals 20 times a sub x. And a sub x is 0 because I assumed it was not moving. So the force of friction equals 180. Is that less than 137? No! Okay, so our assumption is wrong. And you're like, I already knew this. I know, there's a reason I'm teaching it to you this way. Because sometimes you actually have to know what's going on, both physically and mathematically, and it's fine if you can do it without all this extra stuff, but I won't sleep tonight unless I know that I at least made an attempt to show this to you. Okay, so we make an assumption that it's not moving. So that's not going to work. So now we have to make an assumption that it is moving, I guess. That would be the only thing that makes sense. So since it is moving, then that means the force of friction is now the kinetic friction times the normal force, which was 0.6. Okay, so 0.6 times 196.2. Okay, so now we know that the friction force is 117.72. Okay. So now we've got the sum of the forces in the x is 180 minus force of friction equals 20ax, and that's not 0. Not 0. Okay, now if it's moving, you have to put in that 117.72. Okay, because that's exactly what it is. There's no like has to approach, blah, blah, blah. For the purposes of this class, it's just direct. So now we have an acceleration of 3.114. However, there might be a part of you that goes, but if the kinetic force of friction is 117, you skipped F equals 20, or P equals 120. So if it had been 120, wouldn't it be moving? Okay, so see this dude here? So the thing is, since it says that this crate is at rest, so it doesn't matter that that force could overcome kinetic friction, because we have to get it moving first. So even though 120 is greater than that kinetic friction, it doesn't matter because it has to be more than that to get it started. So that's why I like to start. So since it says it's at rest, then I like to start with the assumption of that it stays at rest, make sure the assumption is correct, and move on. Does that kind of make sense? If it says it's moving, then yeah, you want to say, let's start with the assumption that it's moving, and then if you get something that comes out as mathematically incorrect, then you go, oh, I guess it's not actually moving because it can't overcome the kinetic friction, and then you've got to figure out something from there. But it's really important to kind of break these out into steps and figure out what you're doing. Okay, this problem is going to be basically the exact same thing. So the idea, though, is just simply, like I said before, that, you know, if you've got a mass here, so you've got a weight and your normal force and your coefficient of, I guess, kinetic friction or whatever kind of friction they've got going here. Is it kinetic because he's actually moving? Yeah. That whenever you come in here, so if this here is at 30 or some angle, boop, 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 and then this angle here. So you've got W sine 30 and W cosine 30, if you kind of look at it from the perspective of this unit system. So now the sum of the forces in the y are negative W cosine 30 plus n, and he's not flying off the surface. So in this case, n is just W cosine 30. So that's the one you're going to use for friction. You don't always automatically use weight for friction. You use whatever portion of the weight is being not allowed through the surface by that normal force. So that's how those become funner. Atomic scale explanations of friction. Well, whatever, it's fine. Okay, 2 blocks do things. Okay, I'm going to come back and do that one separately. Oh, and a crate on an accelerating truck. And snowboarding. Man, they are just hardcore about these. All right, I'll come back and do these separately, but that's a good start.